Good morning and welcome to Tech 259 for Monday, February 22nd. We're going to talk about combined modes of heat transfer today. And the good news is I think you'll find it fairly intuitive, just putting together the things that we've talked about over the past week and a half to 2 weeks, really. But before we do that, in this first video, I'm going to review problem set number 10 about radiation heat transfer and only radiation heat transfer. So I'm going to switch over to my document camera. All right, in problem number 1, we have a boiler in the middle of a room with a diameter of 3 meters. And the room that it's in is 15 meters by 15 meters. And the height of the boiler is 3 meters tall. And the height of the room is 5 meters tall. So picture that in your head. Picture this cylindrical object in the middle of a room. And the cylinder is 3 meters in diameter, and it's 3 meters tall, and it's in this big room that is 15 meters by 15 meters, and the walls are 5 meters tall. So picture that in your head. And we have the surface temperature of the boiler is 200 degrees Celsius. It's pretty hot. Really should put some insulation on there to get that surface temperature down. But anyway, that's what it is. And the walls are 30 degrees Celsius. If the boiler walls, the walls of the boiler, are painted steel with an emissivity of 0.95, and the room walls are painted brick with an emissivity of 0.85. Calculate the heat lost due to radiation. And to make things simple, we're going to neglect the heat transfer from the top and bottom surfaces of the boiler. So it's only the surface of the round perimeter walls of the boiler that we're concerning ourselves with. Just to simplify things a little bit, it's not that much harder to consider the top and bottom, but we just want to make things simple. So it has a little note over here that says the surface area of the boiler here, it's equal to the perimeter of the circle times the height of the boiler, right? So the perimeter of a circle is pi times diameter, and the height is h. So pi dh is the surface area that we're concerned about around the perimeter of this boiler. And here's the parameters that we just talked about with the dimensions, the emissivities, and the temperatures. So how are we going to do this? What are we going to do? Well, we know we're concerned with radiation heat transfer, because that's what it says, heat loss due to radiation. So we're going to have a surface resistance at the wall of the boiler. We're going to have a space resistance between the boiler and the walls. And then we're going to have a surface resistance at the walls. Right? So we're going to need to calculate those first. We'll have 2 surface resistances and 1 space resistance. And then we can calculate our R rad total by including the Stefan-Boltzmann constant and the temperatures, which we know. But do note that these temperatures are given in Celsius, which is probably most common to measure temperatures in either Celsius or Fahrenheit. But remember that when we plug our temperatures in, they must be in Kelvin, or else they're not going to work. The formula's not going to work. So you got to have these in Kelvin. So we'll do that. So using all of that, we can calculate our R rad total. And then once we have our R rad total, then it's pretty easy. Then we just plug it into our baseline equation where we have our delta T and we have our R rad total, and we just divide those two and come up with the total amount of heat transfer. So it's not too bad. It's not too bad. There's some calculations here, but it's really not too bad. This one is pretty straightforward here. All right, so here is all of the given information. It's pretty much just copied down from the problem. But note that I converted to Kelvin right here because we're going to need to plug them into Kelvin. So I think it's a good idea just to convert to Kelvin right away, because that way you're not tempted later on to plug in Celsius. You don't forget to do that later on. So here's the temperature of the boiler in Kelvin, boiler walls. Here's the temperature of the room walls in Kelvin. And now let's go ahead and draw our thermal resistance network. And the thermal resistance network, this is just for radiation. So we know that we have a surface resistance at the wall of the boiler. We also have a surface resistance at the walls of the room. And then we have a space resistance between the walls of the boiler and the walls of the room. How much of the energy released here actually makes it to here, to the walls of the room. So we have our formulas here. These are directly out of the lab manual. 1 minus the emissivity of the wall boiler divided by the area of the wall of the boiler. Not what was I saying? The boiler times the emissivity of the boiler. So 1 minus epsilon 1 divided by A1 epsilon 1. So in the numerator, we have 1 minus 0.95 because that was the emissivity of the boiler walls. And then I had to calculate the area of the boiler. So that's what's just pi dh. So I did that down here. Pi times the diameter of the boiler times the height of the boiler. Pi times 3 meters times 3 meters gives me 28.3 meters squared. Plug that in. And then once again, I have the emissivity of the boiler wall. Plug that in, keep your units, and you'll get 0.0019 1 over meter squared. That is the first surface resistance. Then we have a space resistance, and the formula for that is 1 divided by A1 times the view factor F from 1 to 2. So A1, that's just the surface area of the boiler. So we just did that. That's 28.3 meters squared. The view factor, you got to think about this a little bit. You don't need to look this up in a table. If you did, then I would have given you the table. What you can do to recognize what the view factor is think about any radiation that is released from the walls of the boiler. Where is it going to go? Well, it doesn't have any choice. If you look at this, any radiation that's released by the boiler, it has to go to the walls of the room. These things can't curve. You can't have radiation that is emitted right here and then curves back around. These are electromagnetic waves. They travel in straight lines. So any radiation that is released from the walls of this boiler has no choice but to travel in a straight line, and it will go out to the walls of the room. So what that means, if all of the radiation that is released by this object is going to make it to the other object, which in our case is the walls of the room, the view factor is just 1. All right, so the view factor F here is just 1. So it's pretty simple. Okay, and that's always going to be true. If the body inside is completely enveloped by the body outside, then any radiation that is released by the body inside has no choice but to go to the body outside. It has no choice. All right, so you can always say that if one body is completely enveloped by another body, then you can say the view factor is just 1. That's kind of the simplest case for the view factor. So we plug that in and we solve, and we get 0.0353 1 over meter squared. And then we have our last surface resistance, which is the surface resistance of the walls. So it's 1 minus emissivity 2 divided by A2, the area of the room walls, times the emissivity 2. So 1 minus emissivity 2, 1 minus 0.85. 0.85 is the emissivity of the walls, divided by the surface area of the room walls. So I had to calculate that here. And the surface area of the walls is 15 meters, because that's the length of one wall, times 5 meters, because that's the height of one wall, times 4, because there are 4 walls. 1, 2, 3, 4. So when I do that, I get 300 meters squared is the surface area of the walls of the room. So plug that in, plug in the emissivity of the walls again, 0.85, and you get a surface resistance at the walls of 0.0006 1 over meters squared. Okay, so now we've calculated both of our surface resistances and our space resistance, so we can calculate our surface plus space resistance by just adding those up. R1 plus R1 to 2, that's the space resistance, plus R2, and we get 0.0378 1 over meters squared. Okay, so that's surface plus space, but that's not the total radiation resistance. To do that, we have to plug that into this equation, which is given in the lab manual. What we're going to do to calculate our rad total is to take the surface and space resistance and divide by the Stefan-Boltzmann constant times the quantity T1 squared plus T2 squared times the quantity T1 plus T2. Remember, those have to be in Kelvin. So I plug those numbers in here. Here is the surface and space resistance from here. And here's the Stefan-Boltzmann constant, 5.67 times 10 to the minus 8th watts per meter squared per Kelvin to the 4th. And then I do my calculation here with the temperatures, 473 Kelvin squared, and that's the whole thing, 473 Kelvin. is squared, plus 303 Kelvin, quantity squared. And then that's times the quantity 473 Kelvin plus 303 Kelvin. When I plug that all into my calculator, I get a total R rad total value of 0.00272 Kelvin per watt. All right, so let's take a look at this real quick and make sure that our units make sense. All right, so first of all, think about the meters squared terms. All right, well, I've got meters squared in the denominator of the denominator and in the denominator of the numerator. So if something is in the denominator of the denominator, then really it's in the numerator. And you could even say it's in the numerator of the numerator. So I've got meters squared that's down here, but really it's in the numerator up here. So I've got meters squared times 1 over meters squared right here. So those meters squared terms cancel out. So my meters squared cancels out. And then I've got Kelvin to the 4th here in the denominator of the denominator. When I combine these terms, I'm going to get Kelvin squared. And when I combine these terms, I'm going to get Kelvin. Kelvin squared times Kelvin is Kelvin cubed. So I have Kelvin cubed in the numerator of the denominator, and I have Kelvin to the 4th in the denominator of the denominator. So that will leave just Kelvin in the denominator of the denominator, and we know that is actually in the numerator. So I can move that single Kelvin term up into the numerator like I did right here. And then watts remains by itself. It's still just right there. It's in the numerator of the denominator, which means it's just in the denominator. So my units here are Kelvin per watt. That's my R rad total, and that's most of the problem. All you gotta do then is plug into our basic equation for heat transfer. And we've got our heat transfer, in this case for radiation, equals T1 minus T2. Don't forget to plug it in. Well, actually, in this case, I would plug it in Kelvin just to be consistent, but actually here it doesn't actually matter whether it's in Celsius or Kelvin. But just to be consistent, I'd keep it in Kelvin. And then this is our R rad total, which we just spent a few minutes calculating. So plug those in, and we get 473 Kelvin minus 303 Kelvin divided by 0.00272 Kelvin per watt from right here. And now, look, we're going to have Kelvin in the numerator. We're going to have Kelvin in the denominator. So Kelvin is going to cancel out. And we have watts in the denominator of the denominator. So that's actually in the numerator, which is a good thing because the whole point is to calculate the rate of heat transfer. So that should be in watts or kilowatts. So it's good that our watts term is in the numerator because that's going to be our answer. So I plug these terms into my calculator and I get 62,439 watts, which is about 62.4 kilowatts. So that is number one. Number two is very similar. In fact, it's the same problem, but we just added a radiation shield. So all the dimensions are identical for the room and for the boiler, but all we did is we added a radiation shield around the boiler. And the diameter of that radiation shield is 5 meters. And we need to know the material it's made out of so that we can get the emissivity of that material. It says it's polished aluminum, so it's a real shiny material that makes for a good thermal radiation shield. And it has an emissivity of 0.05. So if it's a polished, shiny material, it's probably going to have a pretty low emissivity. And you'll see that makes for a good thermal radiation shield. So now we want to do the same calculation that we just did, but considering that we have a radiation shield now, so we want to know, okay, now how much thermal energy is being lost due to radiation from the boiler to the walls. And then it says to calculate the reduction in heat loss. Calculate the reduction in heat loss from the addition of the heat shield. So basically, we're going to compare the answer to number 2 to the answer in number 1. All right, so that's the last thing we'll do. So here is number 2. It makes it kind of nice because all the dimensions are the same and the parameters are the same, except for adding this thermal radiation shield. So when we do that, when we add a thermal radiation shield, we add 2 surface resistances because we add a resistance for the radiation coming into the radiation shield, and we add the surface resistance coming out of the radiation shield. So what we have here for our thermal resistance network, we have the same surface resistance at the boiler surface that we had before. We have a space resistance from the boiler walls to the shield. I abbreviated S here for shield. So this is a space resistance from the boiler walls to the shield. And then we have a surface resistance for the radiation being absorbed by the shield. And then we have another surface resistance for the radiation being emitted by the shield. And then we have a space resistance from the shield to the walls of the room. That's S to 2, I have written right there. And then finally, we have a surface resistance of the walls of the room. So you'll notice that some of these are going to be very similar to the ones we just calculated, but we need to go ahead and take a look at all of these and get a number for all of these. So we got to do these one by one. So the first one is the surface resistance of the boiler walls. This is going to be the exact same as we had in number 1 because nothing has changed about the emissivity or the area of the boiler here. So this is actually the exact same. You can recalculate it if you want, but really it's the same number as we had up here because nothing has changed about the dimensions or the emissivity of the boiler walls. So I did that calculation up here, so now I'll just say it's 0.0019 1 over meter squared. Then we have our space resistance from the boiler walls to the shield, and this is actually going to be very much identical to what we had up here because it doesn't really matter what is enveloping the boiler walls. As long as they're completely surrounding the boiler walls, it's going to give us a view factor of 1. So we can plug in these numbers again. That's our area of the boiler walls, 28.3 meters squared. Once again, we're ignoring the top and bottom of the boiler. Our view factor is 1 because the shield is totally surrounding the boiler. So any radiation that is released by the boiler is going to make it to the shield. It has nowhere else to go. So that's why we have a same space resistance here that we did up here, because it doesn't really matter what it is that's enveloping the boiler. If it's completely enveloping the boiler, it gives us a view factor of 1. So here we have the same space resistance as we had up here, 0.0353 1 over meter squared. Here we have a surface resistance for the shield. So we got to plug in the emissivity of the shield. We're given that it is 0.05. And we got to calculate now the area of the shield. So we already know that the area of the walls of a cylinder is pi times diameter. That gives us the perimeter times the height. So pi dh, pi is a constant. The diameter here is 5 meters for the shield, and the height is 5 meters. It tells us that also. Yep, it tells us that. So we plug in those numbers, and we get an area of the shield of 78.5 meters squared. So then we plug that number into our area for the shield here, and then times the emissivity of the shield, and we get a surface resistance for the shield, our first one, our first surface resistance for the shield of 0.2420 1 over meter squared. And then we have another surface resistance for the shield for the energy being radiated by the shield out to the room. And that's going to be the exact same thing. So we don't have to redo that calculation. It's the same as it was up here. So once again, this is the surface resistance for the energy absorbed by the shield on the inside of the shield. This is the surface resistance for the energy being radiated by the shield on the outside of the shield. So you got to have both of these. But it's the same number, 0.2420 1 over meter squared. Then we have a space resistance from the shield to the walls of the room, body 2. And that's going to be 1 over the area of the shield times the view factor from the shield to the room. So our area of the shield we calculated before, 78.5 meters squared. And what is our view factor? Well, the walls of the room are totally surrounding the shield. So any energy that is released by the shield is going to make it to the walls of the room. Whether or not it will be absorbed by the walls of the room, that's a different question, but it will make it to the walls of the room. So our view factor is 1 here. So we plug these numbers in and we get a space resistance of 0.0127 1/meter squared. And finally, we have our surface resistance of the walls of the room, and that's going to be the same as we had up here because the dimensions and the emissivity of the room walls have not changed. So it's 1 minus 0.85 divided by 300 meters squared times 0.85, which gives us 0.0006 1/meter squared. So then we add all these numbers up to get our surface plus space resistance, and you'll see that that is 0.5345 1/meter squared. If you look, I always think it's interesting to take that number and just look at where it's coming from. So where's most of that resistance coming from? Well, if you look at these terms, it's almost all. So, I mean, the vast majority of that number is coming from these two right here. So the two surface resistances of the shield are providing the vast majority of that number right there. You add these two alone together and you'd get like 0.484 1/meter squared. So anyway, I always think that's kind of interesting. It's kind of a qualitative description of what's going on. So there's our surface and space resistance. Now we need to calculate our R rad total. And so you plug in your surface plus space resistance, divide by the Stefan Boltzmann constant, 5.67 times 10 to the minus 8th watts per meter squared times Kelvin to the fourth, times the quantity of T1 squared plus T2 squared. So that's 473 Kelvin squared plus 303 Kelvin squared times the quantity 473 Kelvin plus 303 Kelvin. So you do all that in your calculator. And just like before, we talked about the units up here, but your meters squared are going to cancel out. And all that's left of the Kelvin is a single Kelvin in the numerator. And we still get watts in the denominator. So we've got 0.03850 Kelvin per watt. All right, that's the vast majority of the problem. Now all we have to do is plug that into our equation for heat transfer. So that's our R rad total. Take your T1 minus T2 to get your delta T, divide by R rad total. The kelvins cancel out, and you're left with watts in the numerator, and it's 4,416 watts, or about 4.4 kilowatts. So take a look at the difference between problem 1 and problem 2. In problem 1, we had 62.4 kilowatts being transferred from the boiler walls to the walls of the room. All we had to do was add a piece of sheet metal that's made out of aluminum, like polished, shiny aluminum, around the boiler, and we dropped that down from 62.4 kilowatts to 4.4 kilowatts. That's a huge reduction. And that makes the whole thermal energy system a lot more efficient because, you know, any energy that is lost has to be made up for by burning more fuel. So if I'm losing that much thermal energy, then I got to burn a lot more fuel or come up with a lot more heat somehow, whether it's burning biomass material. Yeah, it says it's a biomass boiler. So you'd have to burn a heck of a lot more biomass material in this case than you would in this case to maintain the same temperature inside the boiler and get the same amount of steam. All right, so that would always apply. It's always better to have a more efficient system. That way you have to provide less energy input, less thermal energy input, regardless of whether that energy input is coming from the sun or from biomass or nuclear or coal or natural gas or whatever. It's always better to have a more efficient system. So your input costs and impacts are lower. So the last part is what's the difference between these two? Well, just subtract 4.4 kilowatts from 62.4 kilowatts, and you get a difference of 58 kilowatts. So you're avoiding 58 kilowatts of heat loss just by adding that heat shield around the boiler. All right, so that's it for problem set number 10. As always, let me know if you have any questions about that. And let's move on in the next video to talk about combined modes of heat transfer.